Molar conductivity is going to increase with decrease in concentration. Conductivity for a solution whose concentration is almost equal to 0, that is called as limiting molar conductivity. Coleridge's law, which will help you in calculating the limiting molar conductivity of a weak electrolyte. So degree of dissociation means to what extent the dissociation is taking place. Hello everyone, this is Ambli Unnakrishnan from the Department of Chemistry. So today I am back with session 6 of the chapter Electrochemistry. So in the last session we have discussed conductivity of a solution. We started off with the resistance, resistivity, conductance and then moved on to conductivity. And we also studied how we can measure the conductivity of a solution. Right. So in today's session we are going to study another topic, that is molar conductivity. And based on that we have a law, very important law called as Coleridge's law, from which you can expect numerical questions, right? So, beginning with molar conductivity. So, we have already studied what is conductivity, the symbol of that, unit of that, all that. Now, what we are going to study is molar conductivity. So, from that name itself, you can say molar conductivity related to 1 mole of a substance or related to 1 molar concentration of a substance, right? So, let us see. Molar conductivity is defined as the conducting power of all ions produced by the dissociation of 1 mole of an electrolyte dissolved in a given volume of the solution, and it is denoted by the symbol lambda m. So, lambda m stands for molar conductivity. This m stands for the molar conductivity. So, it is also conductivity itself, conductivity by the ions present in an electrolytic solution. The conductivity of those ions when electrolyte we are taking will be 1 mole. We are taking 1 mole of electrolyte. What will be the conductivity? That is called as molar conductivity. I hope it is clear. It is related to the conductivity of the solution by the equation lambda m is equal to K by C. So, this is a very important equation. Lambda m, that is molar conductivity, is equal to conductivity, that is your normal conductivity, divided by the concentration of the electrolyte. So, this is how we can relate molar conductivity and conductivity. Okay. So, when the concentration is 1 molar, conductivity becomes molar conductivity. Both of them will become equal. Alright. So, this is the equation lambda m is equal to K by C. And we also know that concentration is inversely proportional to volume. So, we can also write this equation as K into V. Right. So, that is what is shown here. Either lambda m is equal to K by C or K into V, because concentration and volume is inversely proportional to each other. So, this is a relation which relates molar conductivity and conductivity. Now, in the above equation, if K stands for conductivity, that is kappa, okay. Kappa is expressed in Simon meter inverse and the concentration in mole per meter cube. Then the unit of molar conductivity are in Simon meter square per mole. So, then the equation that you have to use is lambda m is equal to K, lambda m is equal to K by 1000 into C. So, we already know the equation lambda m is equal to K by C, but we have to use 1000 also in the denominator, and you have to be very careful which is the unit it is going to be. When conductivity is given in Simon per meter, concentration is given in mole per meter cube, and molar conductivity will be in Simon meter square per mole, then you have to use this equation. Now, if Siemens per centimeter is the unit of conductivity, there it is Simon per meter, this is Simon per centimeter as the units of kappa, and mole per centimeter cube will be the unit of concentration. The unit of concentration, then the units of molar conductivity will be Simon centimeter square per mole. Okay. Then the equation will be lambda m is equal to K into 1000 by C. I hope this is clear. So, what is the difference? When molar conductivity is expressed in meters, it will be K by 1000 into C, and when molar conductivity is expressed in terms of centimeter, it will be lambda m is equal to K into 1000 by C. So, you have to remember these two equations while you are solving the numerical. So, I hope the relationship between molar conductivity and conductivity is clear for you. Now, variation of conductivity and molar conductivity with concentration. So, we have already studied this equation lambda m is equal to K by C. So, this conductivity as well as molar conductivity will vary with concentration. Now, how they are going to vary with concentration? It is different. Molar conductivity behaves in a certain way and conductivity behaves in another way. Let's see. Conductivity, that is your kappa, the normal conductivity, always decreases with decrease in concentration. It decreases with decrease in concentration, both for weak and strong electrolyte. So what is a weak and strong electrolyte? Weak electrolyte means it will not completely dissociate into its ions. Strong electrolyte will completely dissociate into its ions in aqueous solutions, right? Now, this can be explained by the fact that the number of ions per unit volume that carry the current in a solution decreases on dilution. So, regarding conductivity, we are talking about conductivity. So, conductivity means what we have discussed. In an electrolytic solutions, ions will be present. Due to the presence of these ions, it will conduct electricity. Yes or no? Now, what is happening here? As we are decreasing the concentration, decreasing concentration means what? We are increasing the dilution. So, can I say that concentration is inversely proportional to dilution? Yes, right. When I am adding more and more water, what is happening? Dilution is going to increase, concentration is going to decrease. So, from this, can I say that when dilution increases, conductivity decreases, as well as when concentration decreases, conductivity decreases. So, this is what you have to remember. How does conductivity and concentration will be related to each other? When concentration decreases or else dilution increases, conductivity also decreases, right? Now, molar conductivity increases with decrease in concentration. It was inversely proportional. This is because the total volume of the solution containing 1 mole of electrolyte also increases. So, this is the reason. The total volume consisting of 1 mole of electrolyte will increase. Volume is going to increase. So, in that case, molar conductivity also increases. So, molar conductivity, how does it relate? Molar conductivity is going to increase with decrease in concentration. That means, can I say molar conductivity increases with increase in dilution also? Yes or no? When concentration decreases, dilution increases. Hence, molar conductivity also increases. So, you can remember conductivity increases with increase in concentration, right? And molar conductivity increases with decrease in concentration. Okay, it is inversely proportional. Now, moving on to the molar conductivity variation with concentration. Now, as discussed, for a weak electrolyte as well as strong electrolyte, molar conductivity is going to increase with decrease in concentration, or else it is going to increase with increase in dilution. But the reason by which for a weak electrolyte is going to increase and for a strong electrolyte it is going to increase is different. So, we are going to study in detail about that. So, first of all, what is an electrolyte? What is a weak electrolyte? It is an electrolyte which does not dissociate completely into its ions. For example, let's take acetic acid, which is a weak electrolyte. It does dissociate into CH3COO minus ions and H plus ions. But what you have to understand is all the acetic acid is not going to completely dissociate into CH3COO minus acetate ion and H plus ions in the presence of water. Few of it will remain as CH3COOH itself. Okay, so what is happening? There is not a complete dissociation taking place in the case of a weak electrolyte. Now, the degree of dissociation of weak electrolyte increases upon dilution. Now, what we are going to see is what is the reason why? Because the molar conductivity is going to increase with dilution. So, what is happening here in a weak electrolyte? The degree of dissociation of weak electrolyte increases upon dilution. So, this is an example of a weak electrolyte. I am going to add more water to it. So, what happens? It will become more diluted. When more diluted, what is going to happen? The dissociation, that means acetic acid, more it will get dissociated. More number of ions I am going to get. More it will get dissociated. More CH3CO minus and H plus will be formed. Hence, the number of ions in the solution increases. Thus, molar conductivity gradually increases on dilution. So, I hope the reason is clear. In a weak electrolyte, when we are increasing the dilution, molar conductivity also increases, because when we are increasing the dilution, what happens? More number of ions is formed, because more dissociation is going to take place of the weak electrolyte. That means already some acetic acid will be present and already some ions will be also present. Now if we are diluting it, more of this acetic acid is going to get dissociated, more number of ions you are getting. More number of ions means, of course, molar conductivity is going to increase. So that is the reason in a weak electrolyte. Now when we see the graph for a weak electrolyte, this is the graph for a weak electrolyte. It is going to be a steep increase, which you can see slowly. As see, this is a graph between concentration and molar conductivity. So this way the concentration is going to increase. So this way the concentration is going to decrease, or else I can also say dilution is going to increase. So when dilution is increasing, what is happening to the molar conductivity? It is increasing for a weak electrolyte, and the reason is clear, because the number of ions is increasing. Now moving on to a strong electrolyte. Strong electrolyte is completely ionized in concentrated solution. So what is a strong electrolyte? It will completely dissociate into its respective ions. For example, if I am taking sodium chloride in water, it dissociates into Na plus and Cl minus. All the sodium chloride dissociates. It completely dissociates into Na plus and Cl minus ions. The ions exist as ion pairs and it is not available for conduction. Upon dilution, the number of free electrons will increase and the velocity of ions also increases. Thus, molar conductivity increases on dilution. So, what is happening here? The strong electrolyte, it will dissociate into Na plus and Cl minus. Now, you have a positive and negative ion here which will exist as a pair. Right? It will exist as a pair because it is positive and negative. Now, when we are increasing the dilution, what happens here is the number of ions is not going to increase because already all the NaCl is dissociated. So, the number of ions is not going to increase. When we are diluting it more, what happens is this pair will get split up. The force of attraction between Na plus and Cl minus will decrease and it will exist as two different ions. It will not exist as a pair. The attraction between them will become less and more number of ions will be available. Right? The number of ions will not increase, but you are going to get separate ions. The pair will not exist. You can get Na plus separately and Cl minus separately. Because of that, the velocity, the speed with which these ions are moving will increase and hence the molar conductivity increases. So, to summarize, in weak electrolytes, limiting molar conductivity increases with increase in dilution, because on dilution number of ions is going to increase because the dissociation of the substance is going to increase. That is, your weak electrolyte is going to increase. Dissociation increases, more number of ions is formed, hence molar conductivity increases on dilution. Coming to strong electrolytes, also molar conductivity increases on dilution, but the reason is here the number of ions is not going to increase, but the force of attraction between the ion pairs is going to decrease and hence all of them are going to exist as individual ions. Hence, number of free electrons is going to increase and because of that velocity is going to increase and molar conductivity increases. Right. So, you can see the graph here also. This is for a strong electrolyte. As the concentration decreases or dilution increases, molar conductivity is slowly increasing. Right. You can see the molar conductivity increasing. KCl is an example of a strong electrolyte. Okay. Now, coming back to this, increase in molar conductivity due to dilution for a strong electrolyte is due to increase in speed of ions. In case of weak electrolyte, it is due to increase in number of ions and the speed of ions. I hope it is clear. Right. In weak electrolyte, it is due to increase in number of ions. In strong electrolyte, it is due to increasing number of free electrons. In case of weak electrolyte, it is due to increase in number of free ions as well as the increase in speed of ions. So, I hope the graph is also clear for you. Now, coming to the next important concept, that is limiting molar conductivity, represented by the symbol lambda naught m. Right, lambda m is molar conductivity, lambda naught m is limiting molar conductivity. Now, when the concentration approaches to 0, the molar conductivity is known as limiting molar conductivity. So, conductivity for a solution whose concentration is almost equal to 0, that is called as limiting molar conductivity. So, what do you have here? Yes, this is for a weak electrolyte, we have already discussed here. So, we have already discussed this graph. As the dilution increases, the molar conductivity also is going to increase. in the case of a weak electrolyte. But what can you see here? The graph is not ever touching the y-axis. Yes or no? It is not touching the y-axis. But coming to strong electrolyte, what is happening here? As dilution increases, molar conductivity also increases, and finally it reaches a point here wherein it touches the y-axis. So from there, what you can understand, it is the molar conductivity. This point is the molar conductivity wherein the concentration of the solution is approaching 0. Okay, so when we are diluting the solution, this is increase in concentration, this side will be decrease in concentration. So dilution is increasing, and finally we have added that much amount of water that the concentration of the electrolyte will be very negligible, it is almost equal to 0. Then the corresponding molar conductivity is called as limiting molar conductivity, and we can calculate it for a strong electrolyte. But it is not able to calculate directly for a weak electrolyte. From this graph itself you can see this is not touching the y-axis. Then how can I calculate the limiting molar conductivity, right? For strong electrolytes, lambda m increases with dilution and can be represented by the equation. So, how you can calculate the limiting molar conductivity of a strong electrolyte using this equation? Lambda m is equal to lambda naught m minus A root C. Lambda m is the molar conductivity, lambda naught m is the limiting molar conductivity, A is a constant and C is the concentration. Okay, so this equation is called as Debye-Huckel-Onsager equation. So this is also a very, very important equation, Debye-Huckel-Onsager equation. It gives a relationship between molar and limiting molar conductivity for a strong electrolyte. So how you can calculate the limiting molar conductivity of a strong electrolyte? Using this equation. And from the graph, I hope it is clear. Where the concentration is 0, the corresponding molar conductivity is called as limiting molar conductivity. So this we can calculate it using this equation for a strong electrolyte. Now, how do we calculate it for a weak electrolyte? Weak electrolyte cannot be directly calculated. Hence, we are going to use the values of strong electrolyte and then we can correspondingly calculate the limiting molar conductivity of a weak electrolyte. So with that, we are going to study an important law which is called as Kohlrausch's law, which will help you in calculating the limiting molar conductivity of a weak electrolyte. So let us see at infinite dilution. Infinite dilution means when the concentration is very, very less. Okay, so for a weak electrolyte, what you have to understand is when the concentration is very less or the dilution is very high, it will be really difficult to calculate the molar conductivity. That is why we are using the values of strong electrolytes, right? The electrostatic attraction between the ions is negligible. Hence, each ion makes its own contribution to the total conductance. So, what happens when it is highly diluted, when the concentration is very less, each of the ions is going to behave as an individual ion, right? There will be no pairs. All the positive and negative ions is going to behave individually and all of these ions is going to contribute to the conductance, right? Now, the law states that, so this, what is the statement of the law is also very important and how to apply it is also very important. So, the law states that at infinite dilution, limiting molar conductivity of an electrolyte can be represented as the sum of molar ionic conductivity of anion and cation of the electrolyte. So, the law states that at infinite dilution, limiting molar conductivity of an electrolyte. So, let me take the example of HCl, limiting molar conductivity of electrolyte at infinite dilution when the concentration is almost equal to 0. It can be represented as the sum of molar ionic conductivity of anion and cation of the electrolyte. So, which is the anion and cation of the electrolyte? H plus and Cl minus. So, the limiting molar conductivity of the electrolyte can be represented as the limiting molar conductivity of H plus limiting molar conductivity of Cl minus. So, I hope it is clear. Now, let's take another example, lambda naught, that is limiting molar conductivity of acetic acid. It will be the sum of limiting molar conductivity of acetate ion plus limiting molar conductivity of H plus ion, because that is the anion and cation present here. So, if we know the values of the limiting molar conductivity of the ions, we can calculate it for a weak electrolyte. So, how we are going to do that? Let's see according to Kohlrausch's law. Weak electrolytes have lower degree of dissociation at higher concentration, and hence for such electrolytes, the change in limiting molar conductivity with dilution is due to increase in degree of dissociation. So, near lower concentrations, limiting molar conductivity increases steeply on dilution. So, we can see in this graph, right, it is going to steeply increase with high increase in dilution. Now, the limiting molar conductivity for weak electrolyte is determined using Kohlrausch's law. Now, how we are going to calculate is what we are going to see here. Now, for example, we have taken limiting molar conductivity of ammonium hydroxide can be calculated. Ammonium hydroxide is a weak electrolyte. It can be calculated by knowing the limiting molar conductivity values of strong electrolytes like ammonium chloride, sodium hydroxide and sodium chloride. So, how we are going to calculate? Let me discuss here. So, for each of these electrolytes which is written, we can write it in the form of sum of its ions, right? So, limiting molar conductivity of NH4Cl will be limiting molar conductivity of NH4 plus, right? The ions present here is NH4 plus and Cl minus. So, it will be sum of NH4 plus and Cl minus, right? Now, limiting molar conductivity of NaOH will be sum of limiting molar conductivity of Na plus and limiting molar conductivity of OH minus. Now, the next one is limiting molar conductivity of NaCl will be lambda naught m of Na plus lambda naught m of Cl minus, right? So, now we know all these three, right? It is strong electrolytes, we can calculate them and we'll be knowing the values of these three. Now, the question asks you, or this example asks you to calculate the limiting molar conductivity of ammonium hydroxide NH4OH. Now, to calculate this, which are the ions that I require? I need NH4 plus and OH minus. Those are the two ions that I require. So, where out of these three strong electrolytes I can find NH4 plus? It is this one, that is ammonium chloride. Now, out of these three strong electrolytes, where I can find hydroxide ion OH minus, that is this particular equation, that is the second one, right? So, what I am going to do is I am going to add these two equations. Now, if I am adding these two equations, I will have NH4 plus ion, I will have Cl minus ion, I will have Na plus ion and I will have OH minus ion. But what is that I require? I require only NH4 and OH minus, NH4 plus and OH minus. So, the Cl minus and Na plus is going to be extra. Yes or no? So, we can subtract that. How we can subtract that? Using this third equation, because it is having Na plus and Cl minus. So, what does that mean? Lambda naught of ammonium hydroxide, I can write it as sum of lambda naught of NH4Cl plus lambda naught of NaOH minus lambda naught of NaCl. So, NH4Cl can be written as NH4 plus plus Cl minus. Yes or no? And NaOH is written as Na plus and OH minus. And minus NaCl means you have minus Na plus and minus Cl minus. So, what is happening here? Na plus and minus Na plus gets cancelled. Cl minus and minus Cl minus gets cancelled. So, what you have here? Finally, you will get lambda naught of NH4 plus and OH minus. That's it. So, what you have obtained here? From the three values of strong electrolytes, you were able to calculate the lambda naught m of a weak electrolyte. Now, moving to the next part, that is degree of dissociation. So, it is the ratio of molar conductivity as a specific concentration to the molar conductivity at infinite dilution. So, degree of dissociation means to what extent the dissociation is taking place. So, how you can calculate? So, the symbol for it is alpha, which is equal to, or degree of dissociation can be calculated by molar conductivity, that is at any concentration, divided by limiting molar conductivity. So, this is a very important equation to remember. Degree of dissociation is molar conductivity divided by limiting molar conductivity. And Ka stands for the dissociation constant. Okay, Ka stands for the dissociation constant, which is another equation to remember. It is C alpha square by 1 minus alpha, wherein alpha is degree of dissociation, C is the concentration. So, you have these two equations which you have to remember. First one is degree of dissociation and next one is the dissociation constant. I hope it is clear, right? Now, moving on to the different applications of Kohlrausch's law. Using Kohlrausch's law, it is possible to calculate the limiting molar conductivity of any electron electrolyte from its individual ions. We have already discussed this. And for weak electrolyte, it is possible to determine the value of its dissociation constant using lambda m and lambda naught m at given C, using this equation. So if we can find the molar and limiting molar conductivity of a weak electrolyte, we can calculate its dissociation constant as well as degree of dissociation, right? So in the next class, we are going to move on to the last topic of the chapter, batteries and then corrosion. So I hope the concepts that I have covered in this session is clear for you. So that's all for today. Thank you.